Why event loop? Because the event loop is a code construct that allows you to process an input-output data asynchronously. This means that the processing of each incoming or the outgoing data stream may not block each other. Let's get in more detail. How do you think most of the time a particular server does when it's work? The answer is waiting for incoming connections or execution of some request for third-party servers. For example, we have a web server that expects incoming connections from clients. Our server is written in a synchronous style. It means incoming or outgoing the executable event will be executed in turn. For example, 2 requests from different clients and different browsers came to our server. Call them Client 1 and Client 2. Client 1 sent some request earlier than Client 2, and until we finish processing the request of Client 1 and return some result, Client 2 will be just wait. This often means that Client 2 browser will wait. Page loading will be longer. This is the classic representation of the implementation server in synchronous style. This problem is solved by the asynchronous implementation of the server, and the event loop helps us on it. Event loop can allow us to handle millions of clients very quickly. This is not parallel processing as if we developed our server using a multi-threaded or multi-process style. This is a different approach. Let's understand how the event loop works. Event loop is a code construction that is substantial due to the cycle and, as often happens, to generators. Although implementations may vary in different programming languages. To simplify, event loop is a cycle of enumerating incoming and outgoing events, which does not immediately process these events, as in the case of synchronous style. Event loop works differently. An event loop is an endless loop that takes events from the queue and somehow processes them. And in some intervals, looks if any I/O events have occurred, or if any timers have not expired, then they add an event about this to the queue in order to process them later. For each I/O request, a so-called task is created. This task is stored in RAM and is awaiting execution. This task has all the information about request which processed event loop. Task: this is a kind of delayed execution of a request for the future. It will be performed sometime later. Maybe right away, but maybe after a couple of seconds or in rare cases even minutes. This task will be executed at that moment when it is convenient for the server or its developer. It often happens that tasks are executed at the moment when the event loop can process it at the moment. That is, if the event loop is not too clogged with requests. The trick is that creating tasks does not mean processing them. By creating tasks, we can immediately send the client some kind of response so that his browser not in standby mode. It often happens that instead of the browser, the front-end part of our site sends requests and periodically send requests to our server for some data so that the user does not have to do it himself. This allows you to create dynamic sites and handle many clients at the same time. But I digress. After the task has been created, it will wait until the event loop can process it, and after the task has been processed, we can get the results of its work through the so-called callback. This is a certain function that accepts the results of a task, and further from the function we can continue our processing. For example, return result on the front-end part of the client browser using WebSockets. Asynchronous code implementation requires an approach that is different from a synchronous approach. Since in the asynchronous approach we should be able to work with the event loop and build the server architecture around it. And this obliges us to adhere to some design rules. These rules may differ in different programming languages, but one detail exists in almost all programming languages that support an asynchronous paradigm. This is async, await special syntax. Async is placed in the function declaration, and this syntax tells the interpreter or compiler that the function is asynchronous. By the way, in Python asynchronous functions are called coroutines. Await is placed inside asynchronous functions or coroutine, in those places where we mean potentially convenient places for temporal transfer of control of execution, for another asynchronous function or coroutine. For example, we have 2 different asynchronous functions. Function A and function B, each of them has 2 await pointers. In event both functions got the loop, but function A came first, and a little later function B followed. Both functions received some input from the client. This data unique, so the event loop created one task for each asynchronous function. Task A is executed first, the function is called, the input data is recognized, which she received from the client, the code of the function itself is read line by line, and at some point the interpreter or compiler encounters an await pointer inside the function A. The interpreter or the compiler sees it, temporarily leaves this function and goes to task B. It executes function B until it encounters the await pointer, and then returns again in task A, and will continue to execute the code that is described after the first await pointer. And it will do so until it reads all the code, jumping on asynchronous functions between tasks until each task is fully executed. While both tasks are executed, another request from the client and event loop will create task 3. And the processing of this task will begin only at that moment, when there will be an opportunity. In such an asynchronous implementation based on the event loop and task, there is also a kind of execution queue. If in the synchronous view the queue was clients, then in asynchronous implementation, the queue is task background coroutines that do not cause discomfort to anyone. The client does not wait for page loads due to other clients, and the server processes a potentially larger amount of data input-output at a time. Profit. Everyone is happy. Asynchronous code implementation is often used on servers with heavy input-output loads. This is the best implementation at the moment as it is executed in the main. It does not require parallelization, and can work comfortably with relatively small computer resources. This is a great alternative to zooming, by buying more expensive hardware and renting more servers in the data center. By the way, asynchronous code execution is closely related to such a term as concurrency. I'll talk about this in another video. That's all. I want to recommend David Beasley's Topics of Interest, Python Asyncio. This is the Codefather Labs channel. I hope you enjoyed this video. Subscribe to watch the latest education videos. See ya.